That's a good question.
Were you going to wait?
Yeah, right.
It's on.
It is on. Great. People watching the Tassie lecture videos, just the first thing they're going to hear over and over again is the mic on?
Yeah, you're right. The reason why I'm not getting this is Apollo is because of the new chat.
Ready to go?
Yep.
All right, let's get started with the last session of the day. Tom will tell us a little more about Lorentzian methods in field theory.
All right, quick review. So causality in position space correlators shows up as analyticity because commutators have to vanish and commutators come from the discontinuity across branch cuts. Okay, so causality is very directly related to analyticity in position space. And in particular, it tells you that correlators are analytic as long as you maintain a hierarchy in the imaginary part of the times. Another key point was Rindler positivity. And we use Rindler positivity to argue for the positivity of the double discontinuity, the D-disk. So the D-disk is this double commutator in reflection, in Rindler reflection symmetric kinematics. The Rindler reflection is denoted by a bar. I think when I wrote it before, I used coordinates ty, like Cartesian coordinates, ty and x vector. Here I'm going to use null coordinates, uv and x vector, but the reflection is the same. It just flips the sign of u and v, leaving everything else invariant. Then at the end last time, we started talking about, we talked about the average null energy condition. And then I started talking about a specific instance of average null energy, which is these energy operators. So the energy operator is a version of the average null energy, which is up at infinity, Scri plus in Minkowski space. So it's a special case of the average null energy operator. And its physical interpretation is that the energy operator measures the actual energy that is on the display readout in your experiment. It tells you how much energy was deposited in your calorimeter. So in this conformal picture of Minkowski spacetime, the energy operator is the analytic integral inserted up here in Minkowski space. Actually, in conformal field theory, it doesn't matter so much where you put it. In conformal field theory, you can do an inversion, conformal inversion, which takes this operator up at infinity and puts it back somewhere reasonable, like right through the origin. You just have to keep track of all your Weyl factors and everything, and you can do all your calculations that way. But physically speaking, you should think of it as being up at infinity, far away from your experiment where you're collecting light particles. Today, we're going to talk about applications of the ANEC and then the derivation of the ANEC from causality. So the application that we'll discuss is the Hartman Maldacena bounds, which are a famous application of the ANEC to conformal field theory. The idea is the same as these energy correlators that we talked about before. We're in the context of a CFT. We're going to create an excited state by inserting a wave packet made of a local operator. So I'll call this wave packet state O of P. And the exact definition of this is that we integrate d4x. This is in Minkowski, so let's write that R3, 1. So we integrate d4x, e to the I p dot x. Then I'm going to put in a Gaussian factor here, e to the minus t squared plus x squared over sigma squared. then O of X acting on vacuum. So this is inserting some momentum, and the purpose of this Gaussian here is just to regulate things. We only want to create the state near the origin in the space-time sense. So if we go back to our picture of the energy correlator experiment, then this is creating a state by inserting an operator smeared over this region near the origin in Minkowski space. And then that state is going to spread out, and we want to measure the energy correlators in that state. Actually, we'll just talk about the energy one-point function in this discussion. The energy correlators are also very interesting, especially for experiment, but this bound we can get just from looking at one energy operator. So the average null energy condition tells us that in this state, O of P, the energy operator, E of N, O of P, should be non-negative, okay? Because this is example of the NAC, and just for physical reasons, this is the actual number that you read off from your calorimeter, the amount of energy that you measured. To simplify this, so in a conformal field theory, so this is now just some integrated three-point function. So where we're headed with this is some integrated three-point function. And therefore, we can use this inequality to derive bounds on three-point functions in conformal field theory. That's what we're going to do. Let me first simplify this a little bit, write it a little bit more explicitly. So first of all, we're going to choose a time-like momentum. P is omega t hat. And now our integral involves an integral dt of e to the minus I omega t. I'm just going to write the t part of the integral. E to the minus I omega t minus t squared over sigma squared O of t dot 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 acting on vacuum. Okay, there's all the, we're going to have to do all the other integrals too, but I want to do the t integral first. This integral you can do if you take omega, we're going to take omega sigma much bigger than 1. The intuition for that is that we're trying to make a wave packet, and this condition tells you that you have a wave packet with a broad envelope and lots of wiggles inside your wave packet. And under this condition, you can do this integral by saddle point and just plug in the saddle. And the saddle point is at t is minus I delta. Dot, 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 acting on vacuum, where delta is 1/2 sigma squared omega. So, so far, what we've done is smeared over the Lorentzian time direction. And actually, this is a really useful thing to keep in mind in general. Okay, so when we insert local operators in Minkowski space, we always have to smear them. Because if we're going to calculate something like a norm like this, we need to be in a state that has a finite norm. Otherwise, if we hadn't smeared it, it would just be infinity. And the effect of smearing in Lorentzian time is a lot like moving things into Euclidean time. Okay, so that's all we did is we smeared things in Lorentzian time. When you have these wave packets, that's pretty much the same as moving things off into Euclidean time. So there's kind of two ways to think about making normalizable states in Minkowski space. One is to think about smearing in real time, and the other is to think about shifting in imaginary time. Any questions so far? Yeah.
Is there anything that goes wrong with spatial smearing?
What do you mean by goes wrong?
Or, like, is there a reason why we smear in, like, I guess I see maybe why we might want to smear in time, but could we smear in space?
The question is, could we smear in space? And yes, we are going to smear in space. I was just doing the t integral first.
Oh, okay, okay.
Yeah. So generally, usually we want to smear in the open region. Yes.
If smearing in time smooths out some divergences, why do we still have in like Euclidean quantum field theory these OP limits and so on where we get similarities?
The question is, if smearing in Lorentzian time smears out, gets rid of divergences, why do we still have divergences in Euclidean? Well, look at the value of delta. Okay, so like if we took sigma to be, well, let's see. If we tried to localize things, so if we tried to take this operator and put it all the way at t equal, like didn't shift it in imaginary time, just t equals 0, that would be the same as not smearing in time. Okay, so the coincident point singularity that you get in Euclidean space is basically happening because when you have coincident points, that's as if you didn't do any smearing in Lorentzian. Other questions?
Just throw the saddle point itself away because you normalize things anyway.
Sorry?
The saddle point itself, e to the plus sigma squared omega something.
There's some normalization factors here which we don't have to worry about because we're just going to impose positivity. The positive normalization factors, yeah. Yeah.
This interpretation in terms of moving the operator into Euclidean time when you smear, is that sensitive to which way you smear? Is it special to this way, or is that?
The question is it important exactly which way you smear? The answer is yes. I mean, I meant this sort of more of as a rule of thumb that you can kind of think of two different ways of making things normalizable. In this case, it's literally the same. Although we have to be a little careful with this expression. So like, we have to be careful because there could be other operator, like I kind of pretended this was just a function. This is an operator. It's not really a function. I pretended it was a function. And when we take this and we try to use it in a correlation function, we have to be careful about where all the other operators are. Are there any branch cuts? Like what did we do? When did we move past those branch cuts, et cetera? In the case where I'm about to use this, that's not a problem. And I think I can explain why once we write the next formula. But yeah. Other questions? Okay, so now we can write out very explicitly what that Hoffman-Maltesena bound is in terms of a 3-point function. It says, let's start by writing the correlation function. So there's O dagger of 0. There's a TUU of UV 0. And there's a O of T equals minus I delta Y X. So what I'm doing here is I'm just writing out this thing by doing the smearing integrals. Actually, there's two smearing integrals here. There's one for this operator and one for that one. But since the Anak operator is all the way at infinity, we have to smear one of them. Only the relative, that's like smearing we're smearing twice, but there's a translation invariance because this other operator is infinity. So we really only have to smear the relative separation of these. And that's the same as just smearing one of them. We're going to take one of the operators and just stick it at the origin. Then we have our annex. So let's turn that into an energy operator. So to get an energy operator, we take v to infinity, and we integrate du. Okay, so we have an operator at 0. We have an Anak operator at infinity. That's our energy operator. And then we have to do the last amount. We have to do the remaining smearing on this insertion of O in momentum space. So that is integral dy dx. At this point, I've dropped there was also a wave packet. There was also this Gaussian wave packet. Sorry, there's a question? Yeah. It's redundant to smear both of them because we really only have to, all these correlators only depend on the difference, only depend on the distance between them. So we would just get an overall factor if we smeared. Yes?
You have three operators, and at some point the left operator is going to be light from the stress tensor. So presumably we want it at minus I delta 0 plus I delta.
Good. Yeah, sorry. The point was that we should have put this one at plus I delta, and that's correct. So this one, I'm going to put it plus I delta. It's just the other smearings. We could put we can do comma 0, comma 0. We don't have to smear the other things. Yeah, thanks. Because otherwise we would have an ambiguity in interpreting this correlation function because of the operator ordering. Well, actually, I could leave it at 0. I could have left it at 0 because I wrote the orders. I wrote the operator order in this way, like this operator and then that one, and then this one. And that's implicit that you've moved this one a little the positive imaginary time. So it's the same, but yeah, we could smear that one in time. Other questions? Okay, I've dropped the last. There was this Gaussian term here, e to the minus x squared over sigma squared. I've dropped that here. I don't need it anymore. At this point, I'm allowed to set sigma to infinity, the width of the wave packet. The reason I'm allowed to do that is because this integral is finite as written, and so I might as well just set it to infinity. The role in life of that Gaussian wave packet, the only role in life of that Gaussian wave packet, is to ensure that I can switch the order of limits here. I've switched a limit with an integral, and it's by putting in that Gaussian wave packet that, if you think carefully through this, that's what allows you to switch the limit and the integral. But now that I've switched them, I can just drop it and write the integral this way. Now, this is a very explicit expression written as an integral of CFT 3-point function. And as we've learned in David's lectures, CFT 3-point functions are completely known to some coefficients. And therefore, the ANAC, or the energy bound, places bounds on the 3-point coefficients that showed up in David's lectures. Yes?
So you commuted, just so I understand, you commuted the limit in B by inserting the sigma, the wave packet. But then don't you have to know you can commute the limit in sigma with all these integrals?
Sigma.
Because you said you took the limit as sigma goes to infinity.
Yes, I'm just declaring that if you think through carefully, that at this point you can take sigma to infinity. It's not immediately obvious, but it's true. Yeah.
Maybe that question is like, do you also take delta to infinity?
Delta?
Delta has the sigma.
Good. So the question is, do we also take delta to infinity? No. We're going to take sigma to infinity holding delta fixed, although it doesn't really matter because we're going to end up doing this integral by residues, and the value of delta is not going to enter anywhere. But I don't want to send it to infinity because it's annoying to have my residue at infinity.
Sorry, could you remind me, which direction you call y?
Y is this direction.
Okay, so the up direction is
Correct. T is the up direction. So you can do these calculations in various dimensions, but to be concrete, let's look at 4-dimensional CFT. And we're going to pick our operator O of x to be a polarization vector epsilon mu nu, T mu nu of x. Now, let's remember from David's lectures that so now we're talking about a stress tensor 3-point function, right? Each of these things was a stress tensor, so we're talking with some integrated stress tensor 3-point function. And in a 4-dimensional CFT, that's almost a completely known function. So T mu nu of x1, T alpha beta of x2, T rho sigma of x3 is equal to some unknown coefficients, which I'll call NS, NF, and NV, times some known functions that you can calculate, for example, using the embedding formalism, although that wasn't the first way they were calculated, it's definitely the easiest way to calculate them. So each of these parentheses is in principle, simple and known function. In practice, they're pretty horrendous. Okay, so when you work through the embedding formalism, this is some function of two x differences, and it has a tensor structure in these 6 indices. So this is some nasty but known function of 2 variables with 6 indices on it. I'm going to call those TTTS, TTTF, and TTTV. I won't write all those indices, but those are some known functions and tensor structures. So in a conformal field theory, the tensor structures are completely known, and it's just these coefficients that depend on the theory, so we have 3 unknown coefficients. You can pick any basis you want for these tensor structures. You could choose different linear combinations. So no one of them is sacred or anything. But there's a nice canonical basis provided by free theories. Okay, and that's the basis I'm using here. So the basis that I picked is one where scalar. Okay, so this tensor structure, this is the stress energy 3-point function scalar. The next one is the stress tensor 3-point function in the theory of a free fermion. And the last one is the stress tensor in the theory of free vector. We're not doing free theory here. We're doing strongly interacting general conformal field theory, where we're just using this as a convenient basis for tensor structures that appear in an arbitrary conformal field theory. And if we have 3 of them, then it spans all possible TTT correlation functions. The coefficients here, NS, NF, and NV, you can roughly think of as number of scalar, number of fermions, and number of vectors, but don't think of them that way because we're not doing free theory. If we were doing free theory, those would be integers, telling you how many of each particle there are. But in interacting theory, they're not integers, and at this point, it's not even obvious that they have to be positive. Okay, is there a question? Oh, I saw a question. No? Good? Okay. So now, at this point, we take this O of x, we take this tensor structure, these 3 stress tensors, we plug it into this integral here. So there's some rather somewhat difficult integral that you have to do. I'm not going to do the integral. Actually, I kind of did the hard steps for you already. We kind of simplified things. You can do the rest using residues and some integral identities. I'm not going to do the integral. But if you take that general CFT structure and you plug it in to the energy bound, so plug and integrate. And you have to do this for all choices of polarization vector. We have polarization epsilon mu nu. So you consider all possible polarizations, you plug that in, and you find the inequalities ns is greater than or equal to 0, nf is greater than or equal to 0, and nv is greater than or equal to 0. So these are the Hartman-Malesheim bounds. If we're talking about free theory, then obviously those are all positive. That's the number of scalars, fermions, or vectors. But this is very non-trivial in interacting theory. And the fact that this looks so simple is just because I knew what the answer was before I started writing the lecture. And so I picked a basis of 3-point functions where it would be easy for me to write down what the inequalities were. It happens to be in this free tensor basis where the inequalities just set the 3 coefficients to be positive. Yes?
How did you get 3 inequalities?
Because of the tensor structures. So well, we have to consider all possible tensor structures, but one way of thinking about why you get 3 is because you can decompose into collinear spin, and there's a collinear scalar, there's a collinear spin 1, and there's a collinear spin 2, and each of those gives you an inequality, so you end up with 3. Yes?
Are these coefficients generally functions of central charge?
Yeah, let me write that formula. The question is whether how they're related to the central charge. So there are 2 anomalies, two conformal anomalies. We'll have more to say about those later, but for now, just accept there are 2 anomalies in 4-dimensional CFT, A and C. And A and C also show up in the stress tensor 3-point function, so you can relate them to these parameters. And the ratio A over C is NS plus 11 NF plus 62 NV over 3 times NS plus 6 NF plus 12 NV. Often the Hartman-Malesheim bounds are stated in terms of the anomaly coefficients. So if you use those 3 bounds on NS, NF, and NV, and you ask, okay, what is the ratio A over C allowed to be, then you can convince yourself that it tells you that you have a range from 1/3, so A over C is greater than 1/3, and less than 31 over 18. So sometimes this is the relevant thing that people call the Hartman-Malesheim bound, re-expressed now in terms of the anomaly coefficients. Another thing it tells you is that A is positive. So the positivity of C in the bottom here, this actually you could derive by positivity of this one you can derive by a much easier method because this shows up in stress tensor 2-point function, so you can use reflection positivity. But positivity of A is actually pretty non-trivial, and this is how you prove it. Okay. So this bound we got just by applying the ANAC to this conformal correlator. One of the most interesting things about this application and the Hartman-Malesheim bounds is the connection to holography. So I'm not going to get into any detail at all in terms of the holographic picture, but I just want to draw the picture. So in the holographic dual description, the calculation that we just described is related to causality in anti-de Sitter space. We've been talking about causality in these lectures, but that was causality in CFT. There's certainly a connection between the two, but now we have to change our point of view a little bit and think about causality for processes happening in ADS. So the relationship is that if we put let's put our CFT over here. So this is the CFT4. And we'll put our ANAC operator. We'll just integrate it. I'm going to choose coordinates where I can just put the ANAC operator like this. So this is an integral over the null ray. Remember I said that in CFT, you can take infinity and do an inversion and put it near the origin. So I've done that implicitly here. When you insert the ANAC, what that does, so now we have our holographic direction in ADS. When you insert that operator, what that does is it creates a shock wave in ADS. Shock wave. So the shock wave is a geometry which looks like ADS in most places, but has this delta function localized null plane where there's some non-trivial metric turned on. Okay, so this light ray operator insert on the boundary is dual or produces this shockwave geometry in anti-de Sitter. And then the calculation you can do in a shockwave geometry is you can send something at the shockwave and see what happens. Okay, so this is starting to push up on the limits of my artistic ability, but let's see how we do here. Okay, so that's supposed to be a null plane. It's like tilted into the board. Does that make sense? Okay. Now what we're going to do is we're going to take a particle from back behind the null plane. Okay, so here's our null plane. We're going to send a particle up and have it hit the null plane. Does that make sense? The picture's not going to make sense if I draw it, but okay, so it's coming up behind the plane, and it hits it right there. So our plane is here. The particle's coming. It hits the shock wave. And when it hits the shock wave, what we would expect to happen is that there's some kind of time delay. So when you have an interaction, gravitational interaction, that leads to a time delay. When everything is consistent, it leads to a time delay. And so what will happen on this picture is that we send in this particle. It hits the shock wave. It gets time delayed and comes out here and then continues on its merry way. And so this shift here, delta V, is the time delay.
How is this time delay related to which part of the ANAC operator encodes the amount of time delay?
So, sorry, say the question again?
Which part of the ANAC operator encodes the amount of time delay?
The question is, which part of the ANAC operator encodes the amount of time delay? Basically, the answer is that when you compare the CFT calculation that we did to this bulk calculation, that delta V is O ANAC O. Okay, so when you go through the holographic dictionary, you end up relating the time delay that occurs in the bulk to this calculation that we just did in the boundary. And therefore, this imposing the ANAC in the boundary CFT is the same, and you can match all this stuff one-to-one. In the case of the Hartman-Malesana bounds for the stress tensor, the dual of the stress tensor is a graviton. So we should think about doing this experiment where you send a graviton through the shock wave. The graviton hits the shock wave, interacts with it in some way. Maybe not even in Einstein gravity. You could do this in higher curvature gravity. And so it interacts with the shock wave in some way. It causes a time delay. And then causality in the bulk is exactly the same as imposing the ANAC in the boundary CFT. And you can derive all the same bounds, NS, NF, and NV. You can get these same bounds actually by a much easier calculation holographically by sending particles through a shock wave like this.
The bulk particle is sent from finite Z location, right?
Yeah, I was imagining doing this picture where the probe particle is at fixed Z throughout the process. It's hard to tell in the picture, but it's just coming straight out. Okay, this is all I wanted to say about Hartman-Malesana, but are there any questions? Yeah.
So in like the ADS3 picture where we have the cylinder and we have like a null way on the boundary, eventually if it goes around it would end up in its own like cone again, so it would be chrono, I guess. So can we then even still apply
Good. So the question is, if we think on the Lorentzian cylinder, then the light rays wind back on themselves and are coronal. So how can we use the ANEC? And it's true that we can't use the ANEC on the ones that wind around, but since we can just phrase everything in Minkowski space, that shows that we can actually also apply it on the cylinder as long as we only integrate one cycle without ever winding back on itself. Other questions?
So the positivity of the ANEC says there can't be time advances, right? That's what delta V.
There can only be time there can only be time delays, no time advances. Did I say it backwards? No. Oh, okay, good. Yes, we don't want anything to go back in time. Yeah.
These conditions have any holographic interpretation?
The three conditions. So the question is, do these have a holographic interpretation? I don't. Other than saying you have one for each polarization of the graviton, that's the only interpretation I could say. If the question is why is it in the free field basis that you end up with nice constraints, I don't have intuition for that. I don't know. Yeah.
If I take the O operator as the generic scalar operator, does it correspond to the scalar particle in the box scattering?
So the question is, if we take the O to be a scalar particle, then, or a scalar operator, does that correspond to a scalar particle here? And the answer is yes. The reason I didn't talk about the scalar is because the bound you get by studying scalars in this context is sort of boring. The bound the scalar three-point function, OOT, has just one coefficient, and that coefficient is the dimension delta. And so we already knew it was positive, and we don't learn anything by doing Hoffman-Maltzan in that context. It becomes interesting when you do things with spin. There are other examples besides the stress tensor. You can do it with currents. There's a whole array of these bounds that you get with currents in various dimensions or with various amounts of supersymmetry. Yes? The question is, do we know of examples where the bound is saturated? And it's saturated in free theory. Two of the bounds are saturated in the scalar free theory. These two bounds are saturated, and similarly for the others. And in fact, there's an argument of Sasha Zhebiev showing that if you saturate the bound, I don't know if I can state the precise argument, but the spirit of it is that if you saturate the bound, then the theory must be free. There might be caveats or fine print there, but roughly. Yes?
I guess we could also have created the shock wave by acting with some other matter operator to get it over the line. So does the positive time delay there imply some kind of positivity for other line operators for them getting over some scalar?
The question is whether we get positivity for other types of line operators. I don't know of an argument that along these lines that gives shock waves and positivity conditions. There is another condition that's believed to be true, which is like a higher spin version of the ANEC, but I don't know of any way of. I don't think I've seen that argued holographically. Okay. So what I want to turn to now is the derivation of the ANEC and connecting it to some of these things that we discussed earlier, which are up on this review board. Before we get into the derivation, I want to discuss another important ingredient, which is the light cone OPE. The message of this will be that the average null energy controls correlators in the light cone limit. So what I mean by that is going to become clear as we go. But here's the limit we're talking about. Here's Minkowski space again with u and v. I'm going to take an operator phi of uv and a reflected operator phi of minus u minus v. And I'm going to take the light cone limit. So the light cone limit is a limit where I bring these two operators to be null separated. Specifically, I'm going to take v to 0 and u to infinity while taking v much less than 1 over u. What that means on the picture is that I'm not just taking the light cone, I'm also taking them far apart, but mostly I'm taking them to the light cone because we're taking that limit first. Take them first to the light cone and then pretty far apart. So let's ask, in this limit, what operators we expect to be important or to show up in the operator product expansion of these two phi operators. So when we do OPEs, we're really just doing dimensional analysis. But what we're trying to do is we're trying to take these, forget that they're far apart for a minute, but imagine they were not so far. What we're trying to do is we're trying to imagine that we took this region of spacetime, we zoomed out and treated it as a local operator or as a sum of local operators. And in order to figure out what shows up in the OPE, we just start writing stuff down. Okay, so let's say there's an operator in here with a bunch of u indices, a bunch of v indices at the origin. So we're going to try to expand the OPE around the origin. And then we have to use dimensional analysis to figure out what kinematics show up here. So there's going to be a factor that's the separation between the 2 points. Minus uv is the Lorentzian, or sorry, the space-time distance squared between them, raised to a minus delta phi. So that's to make up for that's to account for the scaling dimension of the phi operator. And then there's going to be a delta O over 2. That is to make up for the scaling dimension of the O operators. We're just doing dimensional analysis here. And then since we had all these U and V indices down here, let's say we had H of these and H bar of those. Then we're going to, in order to make everything Lorentz invariant, we're going to need a U to the H and a V to the H bar. But now we've kind of messed up the scaling, so we have to put in a factor of, I didn't leave enough room for my factor. Sorry, let me move this over. So U to the H, V to the H bar, and then we have to put in a factor of minus L O over 2 to account for the dimensional analysis that we messed up by putting these in. Okay, so the number of U's and V's, that's fixed by Lorentz invariance contracting with these indices. And then the power of UV, that's fixed by dimensional analysis, just looking at the scaling dimensions of the operators. Now, the important thing here is that when we take the light cone limit, where we take V to 0, we see that this becomes an expansion in twist. Okay, so twist is this thing. Delta O minus LO is called the twist. And what we see is that as V goes to 0, the lowest twist operators with no V indices are dominant. Those are the biggest contributions. So the light cone expansion, the expansion near the light cone, is an expansion in twist. This is different from what happens in the usual operator product expansion in Euclidean signature, what we usually use in the conformal bootstrap. When you work in Euclidean, the short distance expansion is an expansion in scaling dimension. The dominant operators in Euclidean are the operators of the lowest scaling dimension. The dominant operators near the light cone are the operators of the lowest twist. And furthermore, as we take, we're also taking U to be large. Is the question? Yeah.
So in Euclidean signature, when we take the OPE, we need the points to be close together. And here I see that the proper distance is very small, but physically they're still very far apart. So why should I expect, is there a reason I should expect this OPE to work in this?
Good. The question is, they're far apart, how can you use the OPE? And the answer to that is, you can't necessarily, and we have to be careful where we apply this, and it's going to depend in particular on what other operators there are around. So yeah, so we have to be careful where we apply this, but for now we're just going to ignore that, and then when we use this inside a correlation function, we have to come back and make sure that we're doing something that's allowed. So the other thing here is that as we take U large, we have these powers of U here, this U to the H, which means that the dominant operators will be the ones with biggest H. So the most number of U indices. So the biggest H dominates. Now all we need to do is start listing operators and try to figure out which ones have the lowest twist and the largest H. No, this is, I think I'm in general dimensions at the moment. Or general dimensions, yeah. I am gonna go to 4 at some point, but this will, yeah, higher dimensions. Okay, so first of all, the operators of lowest twist are the conserved currents. So the operators of lowest twist are conserved currents. Any conserved current in d dimensions has twists d minus 2. Let's write that over here. And the unitarity bound in CFT tells you that any spinning operator that's not conserved will have a twist that's higher than this. So we can focus our attention on the conserved currents. You can also have scalars, which can have a lower twist than this. However, the scalars don't have any U indices. So remember, we were getting enhancements from these U indices. And so for our purposes, we can just ignore the scalars. So, or scalars, but they won't matter. And I'm just going to ignore them. If you're curious, we can come back at the end and you can ask me why we're allowed to ignore the scalars. Now, in interacting theory, interacting CFT, the only conserved currents are of spin 1 or spin 2. There are no higher spin conserved currents in an interacting CFT. If you assume that there's even one conserved current of spin greater than 2, then you can show that there's actually an infinite number of conserved currents of all possible spins, and you can conclude that the theory is free. So in an interacting CFT, the dominant contributions to the light cone OPE are stress tensor, the null energy TUU, and its null derivatives. du TUU, du squared, TUU, etc. So let's check that this makes sense. Is the question?
Yeah, can they go arbitrarily low in twist by just acting with derivatives? Just take any out.
No, because so when you act with a when you act with a derivative, let's do the counting here. It'll be the same. So this thing, the stress tensor always has dimension d, and it has spin. The stress tensor has spin 2, so the twist here is d minus 2. Good. Now, if we act with derivatives in the u direction, if we act with derivatives, that increases the dimension by 1, because the derivative has scaling dimension 1. And it also increases the spin by 1, because we get one more index down here. And therefore, the twist is the same. So this also has twist d minus 2. And this one also has twist d minus 2. These all have twist d minus 2. So these will all contribute actually in a similar way as we approach the light cone limit. So far, we've just used dimensional analysis to figure out what the important operators are. And the conclusion so far is that the important operators are the null energy and its derivatives. Is the question?
Yeah, usually when we do an OPE, we think about a sum of primaries, but the operators you're drawing are descendants.
That's okay. So the question is, what's up with primaries versus descendants? When I was doing this dimensional analysis, I just was using general operators. At no point did I organize things into conformal blocks or descendants or anything like that. It's true that so that's why I had to list all of these. It's true that at the end of the day, you can always come back and phrase things in terms of primaries. So in this case, the conclusion is that the stress tensor is the only primary that's important. But I was keeping track of the others because we're also going to have to keep track of these descendants of the stress tensor. So we just argued they're dominant, but in fact, you could just calculate the entire contribution of the stress tensor to the OPE. Because we know phi TUU. This is some known function. It was probably in David's lecture. And we know TUU is also a known function that was probably in David's lecture. And so if you know the 3-point function, then you can use it to find the OPE. Because you just say, okay, well, there's a TUU showing up in this OPE. And we just, the general coefficient that will determine, we put a TUU in this OPE with a general coefficient. We plug it in here and we make sure it agrees with our known answer for the stress tensor. These are functions, they're not just numbers. So if we make this whole function agree with this whole function, that completely fixes for us the entire contribution of every stress tensor and its descendant in the OPE. And we can use this to determine the light cone OPE completely. And in d equals 4, here's the answer. 5x bar, 5x. I'm going to normalize this by the phi 2-point function. There's a contribution from the identity operator We've normalized that to be 1. And there's a contribution that looks like delta phi over CT, V u squared, integral du tilde from minus infinity to infinity to uu of u tilde 0, 0, 0x. Yes?
We know the 3-point function completely, meaning we also know the coefficients. We had to.
In this case, we actually do know the coefficient. Yeah, so this 3-point function has only one tensor structure, and its coefficient is fixed by the Ward identity to be the dimension of phi. So this 3-point function we actually know absolutely completely, including the coefficient. Okay, so I've skipped a step here. So let me tell you the step and then see if there's still a question. So before I was writing an expansion in derivatives, right over here. We were just expanding, and we said the operators that we put here should be the stress tensor and its derivatives. What I've done here is I've taken an infinite sum of derivatives. You can find other coefficients by the procedure that I described. I've taken the infinite sum of derivatives and re-expressed it as an integral. It's the same formula, though. This is just this infinite sum of du TUU. And if you take the TUU here and you do a Taylor series of this TUU around the origin, like this is just TUU of 0 plus u du, TUU of 0 plus et cetera, and you do the integrals, you have to be a little careful with the limits and everything, but you can do these integrals, and it's the same expansion we were talking about before. So the conclusion is that, do I still have it up here? Okay, so I claimed in this discussion that we were going to show that the average null energy controls correlators in the Lycon limit, and that's what we've shown. We've shown that the leading contributions to the OPE, as you take operators to be like separated, is controlled by this average null energy operator integral TUU over a light ray. Okay, questions about that? Yeah. Good, I didn't define CT. CT is the coefficient that shows up in the TT 2-point function, and it's related to this. It's related to the anomalies, but that's just what we usually call it. Thank you. Other questions? Yeah.
Could we also have evaluated this phi OPE by seeing them as lying on this t equals 0 slice and then using the Euclidean OPE?
Good, yeah. Yeah, so the question is whether we could have worked in Euclidean. And the answer is yes. So there's a general formula for the OPE in Euclidean. There's a Euclidean formula for the stress tensor contribution to the OPE of phi phi, which looks like some integral of a kernel times t of x. This is a formula that you can write down in Euclidean signature. And another way of deriving this formula that we just did a different way, another way of getting it is just to take the OPE in Euclidean and then Wick rotate everything and evaluate this formula in the Lycon limit in Lorentzian signature. So that will also work. It gives the same answer. Other questions? Now we're going to do the derivation of the ANAC. We've already done all the hard work. You can do this in one board, maybe two. Okay, so the idea is to study the 4-point function So we're going to study a 4-point function psi of t is I delta, phi of uv, psi at t is equal to plus minus I delta. The way to think about this, so let's draw a picture. The way to think about this is that we're using the psi operator to create a state, just like we did in our Hartman type calculation earlier. We're using the psi operator to create a state, and then we're probing that state with some operator phi. And we're going to study this in the same limit that we were just in. So we have our psi operator is inserted off a little bit in Euclidean, so I'll draw it like that. And then our probe phi is inserted in this light cone limit. So that's phi. And now we're going to impose causality on this 4-point correlation function. Sorry, one sec. So causality on this 4-point correlation function is a question of, as this phi approaches the light cone, is everything analytic in the way that it's supposed to be? And the connection to the ANEC is obviously going to be what we just showed, that actually this is going to behave just like the average null energy operator in the same configuration. Is there a question?
You might mention this soon, but this is kind of one thing I was worried about like you have these operators between the phis, the psis. How do you know like the OP radius of convergence?
Yeah, good. So that I'm not really going to get into that. Maybe we can talk more about it later. But the short answer is that when you're in the light cone limit, let's look back at this correlation function here. When you're in the light cone limit, you're expanding in V, and so you can always make it a good expansion by taking V to be small enough. I said good expansion, being a little bit careful here. Okay, it's asymptotic series actually. It's not convergent, but it's still reliable in the limit that V goes to 0. So we're going to be using the OP in a situation where the second term is much smaller than the first. The third term is much smaller than the second, but actually it's an asymptotic series, so it's a little subtle. So I'm going to rename my variable to u equals 1 over sigma. The reason for this is just because having stuff happening at infinity is sort of annoying. So I'm putting infinity at the origin. And I'm going to define the distance squared between these 2 points, the 2 phi points. I'm going to call that eta. And the idea is now to write a dispersion relation in sigma at fixed eta. First, let's write a formula for the discontinuity of G. So by the discontinuity, I mean the same correlator, but I'm going to take one commutator. Yeah. Eta is small because that's the light cone limit. So we're taking eta to be tiny, and then we're going to do a dispersion relation in sigma. Yeah. So I'm defining the discontinuity here. Okay, this is the discontinuity we're talking about. But as we talked about before, there's some way of thinking about this in terms of branch cuts, where this is literally the discontinuity across some cut. And the reason I'm interested in the reason I want to take this discontinuity is what we're going to do is we're going to use this formula. Here, we're going to plug in this formula for the phi OPE. But take discontinuity. If you do this whole thing if you're careful about all the operator orderings, then what you find is the following. If you do one operator ordering, then this U contour wraps a singularity and gives you something non-zero. If you use the other operator ordering, you have some I epsilon shift, and it does not wrap the singularity, and this term does not contribute. So this contributes to one ordering, but not the other. The one contributes to both. And by taking this discontinuity, we pick off the term that we're interested in. So this is approximately eta over sigma times the integral, or sorry, psi integral du tilde tuu psi. This prefactor here, this is just the uv squared that we had before, rewritten in terms of our new variables, eta and sigma. So far, so good? Yeah.
You just said UV squared, but there is VU squared.
Uh-oh. It should be it should be the right thing, whatever. Yeah, thank you, yes. I'm not doing coefficients. Okay? So now, causality. Look back at the review board. Okay, what's causality mean here? Causality means that this correlator is analytic in the appropriate domain. And I'm not going to go through all the coordinate changes and I epsilons, et cetera, but if you sit down and think about this for 5 minutes, then this tells you that this is analytic for sigma in the lower half complex plane. If it's analytic, that means that I can write formulas. So what our goal is to write some contour residue type formula that extract the anic term. And we can do that now that we have analyticity. We can calculate the integral d sigma of the discontinuity over the following contour on the sigma plane. So there's a singularity at sigma equals 0. That's a coincident point. That's where you're hitting a light cone. But we know that it's analytic on the lower half plane by causality. And so I can do a contour integral that looks like this. And if I do that contour integral, that is going to give me 0. Because I'm integrating an analytic function around a closed contour. Well, if that's 0, then its real part is also 0. And the nice thing about that is that the real part, so this is like a half, we're trying to pick a residue. We have this 1 over sigma. And the way you want to pick up is to do a circle around the origin. We can't quite do that here because it's not analytic at 0. But what we can do is we can do a half circle, its real part. That does the same thing, okay? So when we do this real part, then the contribution from the semicircle is going to be our anic term. And so if I split this, I'm going to now split this contour integral into 2 pieces. I'm going to talk about the contribution from the straight part and the contribution from the semicircle. And that gives us the formula psi integral du tilde tuu of u tilde psi is equal to some constant over eta integral d sigma from -1 to 1 of the double discontinuity of G. Let me go back and explain where the different pieces came from. So the curvy part picked off the residue. That was our Anak term. And was the real part of the discontinuity. The real part of the discontinuity is the double discontinuity. So that gives us this formula relating the average null energy to the double discontinuity of the 4-point function. One sec. And now we're done, okay? So the double discontinuity is positive by Rindler positivity, and we've derived a sum rule that relates the average null energy in the state created by psi to something that's manifestly positive. That's greater than 0, and that's the average null energy condition in this 4-point function. Okay, that's a question.
Yes, could you repeat how you get the residues you don't know what's happening in the upper half plane?
That's just the identity. So, okay, so the identity that we're used to is okay, that's the identity that we're used to. But this is also a true identity. You can pick off the residue either by integrating around the origin or by integrating halfway around the origin and taking the real part. So I've just done the residue in that way instead.
Could there be more folds in the other half plane you also pick up?
Sorry?
Could there be more half plane you also pick up by doing this?
Okay, so the question is, could there be stuff going on in the upper half plane? No. Okay, so the answer is that it's actually also analytic in the upper half plane, and it's really only along the axis that you have to worry about this. That's a little subtle because we have to say how we got half plane, et cetera, but it works out in such a way that both terms here are analytic.
It's clear that the origin is no branch cut or...
At the origin?
Yeah.
There actually is a branch cut. There can be branch cuts at the origin here, but it's okay because we didn't deform around that branch cut. What we did is we added a contribution from the top to a contribution from the bottom, and that gave us the double discontinuity, which was actually what we wanted, was the discontinuity across this cut. So that's what we were after. And that sort of ties together all the things that we've talked about. We've got analyticity, causality, positivity, the Anak, they're all showing up here in one big happy sum rule. The broader context here so the goal of this was not just to prove the Anak. Probably we could have proved it using relative entropy or something and maybe proved it faster. That wasn't the whole goal. The goal was really to understand the structure of correlation functions in the Lorentzian limit. And not only do you get positivity here, we also learned that these light ray operators, like the average null energy, are controlling this interesting limit of correlation functions. And in fact, this is a special case of what's called the Lorentzian inversion formula. This is a limit or special case of the Lorentzian inversion formula, which is a bigger, more powerful technique or formula where Well, what the Lorentzian inversion formula does in conformal field theory is it tells you that all of the data of the conformal field theory is hiding or encoded in D-disk. I'm not going to write the formula. It has a similar form, but it has a similar flavor to it. Here we learned that these particular ANAC type contributions could be extracted from D-disk. And what the Lorentzian inversion formula does is in a much more general setting, it says that CFT data is equal to an integral involving D-disk on the right-hand side. And you can extract everything about the theory that way, at least everything above some low spin, like 1 or 2. Okay, any questions? Yeah.
How much of this conclusion over here relied on the fact that we started from CFT intuition?
How much relied on the fact that we're doing CFT? So this derivation is really, strictly speaking, it's a CFT derivation. However, we're in the light cone limit, and in the UV limit, if we have a conformal fixed point in the UV, we can apply similar logic. Whether there's any subtleties in that, I don't think anybody has really worked out all the possible subtleties, but it seems likely that it could be applied to any situation where there's a conformal fixed point in the UV. Speaking of those subtleties, the last lecture tomorrow will be about trying to understand properties of light ray operators and ANAC and applications of to theories that are not CFTs. And I think here's a good place to stop, and we'll do that the last lecture.
Thanks, everybody. There's no fourth lecture today. We'll see you all. And I was just going to remind everybody, although there's no fourth lecture, there is coffee. So if you want some, it's available.